Okay, so first of all, welcome to everybody to this summer school from the Apolo European project. My name is Ana Mirena Cruz. I'm the technical coordinator of this project that leads with Perovskite PV technology devices. So the idea in these 3 days is going to be to give to the students and all the people interested in technology a general overview of what is a perovskite, a solar cell, what are going to be the applications, the main challenges of the technology, and see a final application dedicated to the Apolo project that leads with flexible perovskite PV photovoltaics. So I want to thanks to all the students that are registered to participate in this event. For us, it's very grateful to see how many people we have today and in the rest of the summer. And also, I want to thanks to all the panelists that are going to provide the talks to the students. The Apolo consortium for the support, and of course to all invited panelists that are going to explain a little bit about this new technology and about perovskite solar cells. So I'm going to give the floor to Manuel to introduce a little bit the University of Lisbon that it's doing the support also for this summer. So Manuel, all yours.
Thank you, Ana. Welcome everyone. So unfortunately, we cannot have this school in presence. Otherwise, you'd be here in Caparica. So it's a place right next to Lisbon, but also right next to the beach. So if we had a chance to have this school in person, you could even take a swim, after the quizzes every day. But okay, I mean, unfortunately, we need to we still have the restrictions, so let's do it online. But I think that still, even online, it will be fun, and I hope that you all enjoy and you all learn a lot from this school. The main thing that I just wanted to say is that this is a summer school, so it's not, let's say, a very, it's an informal, let's say, it's quite a very informal conference. So the purpose is for you to learn. Okay, this is the main purpose that we are here, not to present our work or, well, of course, it's very interesting for us to present it, but the main thing is that we want you to be engaged and to take as much knowledge from the talks as possible. So I just invite everyone, even though this is online and via Zoom, I just invite everyone to don't be shy and to participate. So I'm pretty sure that all the speakers here, they would welcome questions or comments even during their talks. So feel free to raise the hand or to put questions in the chat. To interrupt. I mean, this is what a summer school is about. It's not just a presentation where people just throw their knowledge and other people listen. So just feel free to engage and to, if you don't understand something, interrupt. If I don't agree with something, also say it. So that's the purpose that we are here. It's just to exchange ideas and knowledge, and maybe even your ideas can be inspiring for us to think in different ways. So yeah, feel free just to participate anytime, and that's what the school is about. So well, yeah, so again, welcome, enjoy, and have some great days with us.
So it's my time just for some technical things. I'm Joan Gali from Leitat. I'm the communication and dissemination manager for this project. And just will tell you some few things. Just that you have to know that this summer school has been recorded. At this moment, it's recording. So just to inform you about the chat, I think everybody of you knows how to work with the chat. At this moment, some people is already writing in the chat. As Mr. Manuel Mendez told you, use the chat for any questions. You can even send questions directly to the teachers, to the speakers. You can use the arrow just on the bottom of the chat. You can see send to all panelists or directly to whoever. The last point that I want to mention is about the quiz. Every day we have a quiz session about half an hour. How it will work? We are going to send you a link here in the Zoom, not by email. You will see the link in the Zoom application, and you will have half an hour, so until 5 o'clock of the afternoon to finish the quiz session. And that's all. If you have questions or if you have some technical issue, just you can write me an email to Joan at leitat.org. I will write you here in the chat and you will have it. Thank you very much. So Anna, it's your turn again.
Okay, thank you very much to Manuel and to Joan for the introductions. As I mentioned, the idea is to get into the world of perovskite. So the first session today is going to be a perovskite PV general session. So the idea here is to give to all of you an introduction about the technology and about how this technology works and how are the challenges that we need to face to rise this technology to a future commercialization. Okay, so we are going to start with the Dr. Hyun Kim from the EPFL in Switzerland. So Dr. Kim has a PhD in material engineering from Pohang University of Science and Technology in South Korea. He's currently working in the group of molecular engineer and functional materials of the EPFL as a postdoc researcher, and his research focused principally in organic and perovskite materials and their application on photovoltaics, solid-state light drives, and flexible electronics. So today, the idea is he's going to open this summer school with an introduction of what is perovskite technology, including not only solar cells, but also other applications like emitting diodes, in order to give the general picture of the technology. So Dr. Hyun, thank you very much for coming, for being panelist, and to open this summer school. All floor is yours.
Okay, thank you very much for your really kind introduction, and I'm very honored to have a chance to talk here to everyone, students. So yeah, let me start. Let me open this session. And yeah, my name is Ho-Bom Kim, and I'm doing research on basically perovskite optoelectronic devices in the EPFL. And as I said, I'm very glad to be here to give you a talk today. Yeah, if you could see each other offline in person, it would be much greater. But yeah, this is still good. So I know here, and I heard that the audience in the summer school is mostly undergraduate and some of master students. Then some of you might be not very familiar with this topic, and but I'm sure that you are here because you are interested in this perovskite solar cells and materials. So yeah, today I'm going to introduce from what perovskite is to its applications such as solar cells and a little bit of LEDs. Yeah, so then what is perovskite? So actually perovskite is originally the name of mineral, calcium titanium oxide. which was discovered by him, Gustav Rose, and named after by a Russian mineralogist, Lev Perovskite. Lev Perovskite, and now we call it Perovskite. And now we know this is the name of material with this crystal structure consisting of 3 components, basically A, B, and X, and the formula becomes ABX3 like this. So in this structure of ABX3, we have a cation in this A site, which is coordinated to 12 xn here. Like you could imagine each plane in X and Y and Z axis that forms a cuboctahedron. So here, and we have octahedrons as well, in which the B-side cation is coordinated with 6 xn. So then, can we get this structure if you just have these 3 components? No, actually, there are certain conditions that should be satisfied to form this perovskite structure. So the structure formability of this ABX3 perovskite can be estimated by considering this tolerance factor and this octahedral factor. So for this tolerance factor here, the RA, RB, and RX are the ionic radii of ABX ions. And in principle, when this tolerance factor is 1, the ideal cubic perovskite crystal structure is formed. So simply speaking, this tolerance factor determines whether the A-side cation can fit into this cuboctahedral site or not. And on the other hand, the octahedral factor, this also needs to be considered for the formability of this BX6 octahedra. So we can take this plane here, and when we projected this from the top, for example, then we see a hole here, which is the position, which should be the position of this B-side cation. There should be 0.414 of the radius of this xn ion when these anions are closely packed. So therefore, this B-side cation should have a larger value than this one. Otherwise, these xn ions will be overlapped. So in the perovskite solar cells, so rather than the oxide perovskite that they found in the previous slide, the metal halide perovskites are used as a photoactive material, and these are the typical constituents. So in the A site, organic ammonium, such as methylammonium or formamidinium and cesium can be placed, and the B site at the center of this octahedron. Mostly lead ions or tin ions, they are used, and in this X site, this iodide, the bromide, chloride, these halides are used. And empirically, material compositions with this tolerance factor between 0.8 and 1, they are found to be able to be perovskite at room temperature. And regarding the octahedral factor, with the radius of these B-side cations, lead and tin, and they have like around 120 picometer radius. the octahedral factors are all calculated to be more than 0.5, which is larger than this, so that they meet this octahedral condition, factor condition as well. So we can get this stable perovskite materials. And we should talk about how the perovskite solar cells work. Then I can just keep talking about this conventional silicon solar cells to show what the difference is from the perovskite solar cells. The silicon solar cells are based on the PN junction. I guess you took a course of semiconductor device physics, I hope. And simply speaking, we have P-type silicon and N-type silicon bilayer. And at this junction, the electrons from the N side diffuse into the P side, and the depletion region is formed at the center, at the junction. Because of this electron migration, the N side boundary becomes slightly positive, and the P side becomes negative. So the electric field is formed between the charges, which in turn produces the potential difference, what is called the built-in voltage, and the light, and we have to consider when light is coming. So when the light is illuminated, the charges generated in this depletion region swept out from the region and make a larger voltage difference, and then flow of charges, which is current. And how about the perovskite solar cells? Basically, it has a PIN structure, which is a P-type and intrinsic and N-type. And when the light is illuminated, there will be a generation of charge carriers by the photoexcitation in this perovskite layer. And the charge carriers transfer via each interfacial layer. So electrons will be transferred into this ETL, electron transporting layer, and the holes will go to the other side. But the electrons and holes cannot go the opposite directions, because the interfacial layers also act as a blocking layer against the opposite charges. So electrons and holes are collected only to the right contacts, not to lose current. And how we estimate the efficiency of perovskite solar cells, this is the definition of power conversion efficiency. And this is power max, power out divided by power in. And this power in is related to the solar spectrum here. The standard we use to simulate is normally 100 milliwatt per square centimeter, so-called one sun. And the power out is correlated to the VOC and JSC and fill factor. So the JSC, the short circuit current, is the current through the cell when the voltage across the cell is zero. When the solar cell, the VOC, the open circuit voltage, is the maximum voltage available from a solar cell, of course. And the fill factor determines the maximum power from a cell, so in conjunction with VOC and JSC. So for example, we can draw a square here from the JSC and VOC, and another one with this J maximum power point and V maximum power point. And the product of these, this area corresponds to the maximum power of a cell, and the ratio between these two squares will be the fill factor. And this is just for a single unit cell. If you connect the cells in series or in parallel, you're going to have multiplied JSC and VOC, depending on the connection. And what determines efficiency of perovskite solar cells? So open circuit voltage is basically determined by the band gap of the material. Of course, there will be like many factors to impact, but basically, and the open circuit voltage increases as the band gap increases like this normally. But the VOC is, as I said, limited by some factor, for example, charge recombination in the bulk and at the interface. So reduction of non-radiated recombination is important to have high VOC. And for JSC, short circuit current, the photogenerate charge carriers should be well contained and well collected to the electrodes to result in current. In other words, a collection of charge carriers without loss by recombination is important to obtain the high current. So here again, reduction of limiting the non-radiated recombination is important. Why do we use perovskite in solar cells? What is good about perovskite solar cells? I mean, what is good about perovskite material? So at first, it has a high absorption coefficient. It simply means it can absorb a sufficient amount of light only with a thin layer. So in this case, with perovskite, normally less than several hundred nanometers. Oh, I'm sorry. Oh. This optical property is actually based on this electronic band structure of perovskite. So in this perovskite, the band structure is primarily determined by this BX6 octahedra. Here, for example, PBI6. But the contribution of this A-side cation to this electronic property is not very significant because the electronic levels of this A-side cation lie deep inside the valence band and conduction bands. So yeah, it does not make a great impact on this electronic band structure. So when we see this simplest form of lead iodide, PBI2 here, they produce this overlapped structure, orbital structure from their own orbitals, and it becomes the band structure when it comes to crystal lattice in 3D. So again, regarding the origin of the high absorption coefficient, the optical transition type between direct transition and indirect transition, this matters. And many theoretical calculations and experiments have proved that metal halide perovskite mainly have direct band gap. Therefore, perovskite have the high absorption coefficient. And also, perovskites have long charge carrier lifetime and long diffusion lengths. So the photogenerate charge carriers can migrate in a long distance to be well collected to the electrodes without recombination. And lastly, perovskite is defect tolerant. For example, in traditional semiconductors, defect states significantly involves non-radiated recombination. But interestingly, even though perovskite also has defect states, the charge carrier lifetimes or diffusion lengths are exceptionally long in perovskite. So this indicates that this defect states in perovskite are benign electrically and defect tolerant. So. And then, yeah, if you fabricate perovskite solar cell, what would be the maximum efficiency? We should have a look at this Shockley-Kaiser limit, which is the maximum theoretical efficiency of a solar cell. It takes account of the solar spectrum, and based on the calculation, I cannot present the details. The maximum efficiency is 33.7% for solar cell with a band gap of 1.34 electron volt, if I remember correctly. So yeah, this is the limit of JSC and VOC and fill factor as a function of band gap of a material. So, and we have this Shockley-Kaiser limit of efficiency, the black line, for example. When we have a look at this perovskite, but this is not the state-of-the-art one. If you think about the FAPBI3, which is the state-of-the-art perovskite, having a band gap around 1.5 electron volt, we could expect its efficiency goes to go over 30%, ideally, according to this graph. And if you can make multiple junctions, you can increase the efficiency, of course, as you can see. If a single junction solar cell observe this part of solar spectrum up to around like 900 nanometer, the cell can attain like 31%. And if you stack the cells using observers with different band gap in an ideal way, I can achieve 68% in principle. And this type of device is what we call multi-junction solar cells or tandem solar cells. This will be dealt with tomorrow, the day after tomorrow, by Professor Naziruddin, tandem session. So where are we now? So this is the NREL or NREL chart showing power conversion efficiency of solar cells certificated. The efficiency of perovskite solar cells in this chart started from less than 15% in 2013, and now it is 25.5%, which is very close to the efficiencies of silicon solar cells. So now I'd like to introduce how the perovskite solar cells has evolved in chronological order from the first perovskite solar cell, and some works that I think of as a breakthrough. So yeah, this is the first perovskite solar cell, but the structure is a little bit different. I mean, quite different from the state-of-the-art structure. So this is the structure now for this first perovskite solar cell. Inspired by the high absorption coefficient of perovskite, it was employed as a photosensitizer instead of the dye in this conventional dye-sensitized solar cell structure. So as you can see here, this initial structure had a thick mesoporous dioxide layer, and the perovskite covered the surface of this mesoscopic dioxide. But actually, unlike this fully covered dioxide by the dye in this figure, the perovskite actually sparsely covered the dioxide like this in this SEM image. And the problem here was the dissolution of the perovskite, of course, because of this, they still use this liquid electrolyte in this DSSC structure. And this problem was solved by replacing the solid state Hall conductor, yeah, instead of this the liquid electrolyte. So it was like a spiral omitted on top of this perovskite layer. So yeah, the device resulted in this PCE of 9.7%, and more importantly, this substitution of liquid electrolyte dramatically improved the long-term stability of the device, maintaining the PCE over 500 hours. It was a huge improvement compared to the previous one with the liquid electrolyte that only lasted some minutes. And in addition, thanks to this high absorption of perovskite, the thickness of the whole device was significantly reduced. And in this work, instead of mesoporous dioxide, an insulating mesoporous scaffold of alumina was introduced. And this increased the VOC compared to the device using desensitized mesoporous dioxide. The authors claim that the photo-generated charges can stay longer without recombination. This can increase the VOC, they claim. But what is meaningful of this study was that it suggested that perovskite itself is a good electron transporter. So in other words, even with this insulating species in between the alumina, the device worked well. And perhaps people think the use of mesoporous dioxide will not be so necessary. So planetary junction later, without this mesoscopic layer, appeared. I will tell you a little bit more about this later. Yeah, and then people got some like insight that maybe we could increase the thickness of perovskite more. So here we see this bilayer-like layer, partly, as you can see here in this part, in this figure. So in previous work, you may remember that the thickness of the perovskite layer itself was not so exceeding. They are all overlapped like this. Here as well, they all they didn't have the like additional perovskite layer, but here they said like this. They call this bi-continuous nanocomposite. So this work means this work proves that the perovskite layer itself can be thicker. So yeah, and in this work, so we are going like as time goes by. Now we are in 2013. So they firstly show this sequential deposition method. Now we simply call it two-step process. So in one-step process, we put all the precursor together in a solvent to dissolve. But in this two-step process, lead iodide is first deposited, and the subsequent deposition of ammonium halide on the lead iodide can cause reaction to crystallize perovskite. So using this method, they achieved 15%. So here again, this is a one-step process. And you can definitely differentiate this additional layer, like a bilayer type layer. So they, in this work, they introduced new technologies for uniform and dense formation of perovskite layers. So before this work, because of the low vapor pressure of DMF, the solvent, the typical solvent of the perovskite solution, retards its evaporation, and this leads to slow nucleation and rapid growth of perovskite. It was very hard to reproduce uniform perovskite film. So they introduced solvent engineering as well as the toluene dripping, which were greatly successful to facilitate uniform nucleation by rapid solvent remover. The toluene dripping is done after spinning the precursor solution on the substrate. So during the spinning of the substrate, the solution, when you drop the toluene, the solvent of the precursor solution is extracted to result in the uniform and rapid nucleation of perovskite. After thermal annealing, it completes film formation with this compact polycrystalline perovskite layer. And this solvent dripping method has become typical now to achieve highly reproducible and efficient devices. And here, because the narrower band gap of perovskite, for example, here FAPBI3 than MAPBI3, can allow broader absorption of solar spectrum. The use of FAPBI3 has been attempted besides MAPI, MAPBI3. So because the electronic properties of these perovskite films, as you might already recognize, closely related to this film quality. So deposition of dense and uniform film is important and crucial to fabricate high-performing devices. So here they introduced the direct intramolecular exchange of the MSO molecule, which is intercalated in this lead iodide with FAI. So this is to control the kinetics of crystallization, simply speaking. So in this way, high quality FAPI film with large grain size and dense microstructures and flat surfaces was produced. So they reported power conversion efficiency of 20% now using this FAPBI3 perovskite. This chart well summarizes how perovskite solar cells have progressed. So the works that I introduced were mostly about the material engineering with the evolution of device configuration. Now, actually, perovskite was already an ideal material for solar cells. I mean, based on the excellent properties like absorption coefficient, long carrier diffusion lengths, high defect tolerance, etc. So you could focus on this optimization of the materials and processes. But from this point, 21% to 25%, it's been mostly based on this management of trap. Trap is actually a defect. So defect engineering becomes important to improve efficiency further. And there are like different types of traps, for example, vacancy or interstitial defects, substitutional defects, grain boundaries and dangling bonds, etc. Among these trap sites, grain boundary and dangling bonds can act as a deep level trap that should be minimized. So here people have attempted various ways to do so, like to minimize, to reduce the density of defects by doing so-called passivation, trap passivation or defect passivation using Lewis acid or Lewis base, or by introducing this wide band gap materials, etc. And so far, we've been through the solar cells, including this mesoporous structure. Now I'd like to show another structure that I briefly mentioned before, planar heterojunction perovskite solar cells. So this is the structure without the mesoporous dioxide layer. So many electronic devices are being developed toward the flexible configuration for future electronics, but the mesoscopic perovskite solar cells cannot be made flexible because the mesoscopic structure should be sintered at high temperature, over like 400, 450, 500 degrees C, which makes flexible substrates deformed, not available. Therefore, to establish flexible perovskite solar cells, this kind of planar heterojunction perovskite solar cells, which do not use this high temperature processed mesoscopic structure, can be a practical option because it can be processed at a low temperature. This planar heterojunction cells can be divided into two groups according to the layer stacking sequence. The one is NIP from N to P, and the other should be, of course, PIN. I'm not going to talk about these flexible devices because we also have the separate session for it. Yeah, but I will introduce some works about these planar heterojunction devices. Yeah, this is what we looked already. So inspired by this work, in which insulating aluminum oxide mesoporous scaffold was introduced. So I said people questioned if mesoporous dioxide is necessary. And yeah, there have been studies on it. However, I mean, without the mesoscopic structure. However, most studies at the beginning on this type of planar structure use the compact titanium oxide layer, which also needs to be processed at high temperature, like over 400 degrees C, which is still not compatible with flexible devices. So studies on low temperature process with compact layer have been required. So here, these works are about planar heterojunction perovskite solar cells based on the low temperature solution processed tin oxide as an ETL. I mean, the low temperature is like less than 200 degrees C or 150 degrees C, so it does not harm the flexible substrate. And they prove that the low temperature processed tin oxide is an excellent alternative ETL material. And yeah, as I said, this is compatible because it's flexible substrate and the roll-to-roll manufacturing process as well. This is another one using the low temperature processed tin oxide. In this work, they achieved 23.32% certificated efficiency using the low temperature processable tin oxide, and also passivation layer on top of the perovskite. And the passivation method here, this can significantly reduce the defect density, and non-radiated recombination can be suppressed. As they describe in this article, this configuration can be advantageous to demonstrate cost-effective flexible solar cells. And here I show the other stack, PIN, planar heterojunction, so which was first developed in 2013 2013, they brought the structural concept from organic solar cells first. So they used this concept of donor and acceptor. Although the efficiency was much lower compared to the mesoscopic devices at that time, this work had the significant meaning in developing a new design for perovskite solar cells that could be processed at low temperature, like 150 degrees C. And this one in the middle, they demonstrated flexible perovskite solar cells on flexible polymer substrate, resulting in this almost 12% of efficiency. And now, not now, but I think this is published in 2017. I cannot find it. Anyway, now with this PIN planetary junction, we also achieved over 20% of efficiency. So now efficiencies of perovskite solar cells are now good, high, but what we still need to improve is stability of perovskite solar cells. So perovskite material or device can be degraded by light or moisture or thermal stress, these external stresses. But to keep the perovskite and solar cells stable, the engineering of the components consisting of the cell is essential. One of the main reasons for this weakness against these external factors is that perovskite is based on the ionic bond. So the formation of ionic defect is inevitable, and the ion migration occurs, and it should be managed. So there have been various methods, various approaches to improve the stability of perovskites, and use of low-dimensional perovskites, such as quasi-2D or 2D perovskite, can effectively suppress ion migration, so that improve stability of perovskite and devices. So this low-dimensional perovskite is can be formed. I mentioned the tolerance factor. So when the size of the A-side cation is getting bigger at a point, the perovskite cannot maintain its three-dimensional structure, but it forms into this kind of low-dimensional structure. So yeah, if we compare these two systems, 3D and 3D with 2D perovskites, about the ion migration, we can see that the possible pathways of this ion migration in these two systems. So the diffusion barrier energy within this 3D work region would be similar in both systems. But however, the barrier energy for this ion diffusion becomes highly different when it comes to the region of grain boundary. In 3D perovskite, the ions can reach this grain boundary without being required to diffuse across the 2D perovskite barrier layer. So it's kind of a free path, it can just migrate. But with this 2D passivation layer, the ions should overcome the higher barrier energy to get overcome the organic capping in this 2D perovskite region. So this kind of ion migration suppression is important to make the perovskite solar cells, well, of course, as well as LEDs stable. What would be the future for these perovskite solar cells then? As we just discussed, the stability of the devices would be, should be guaranteed to be commercialized, and also the scaling up will be necessary without losing efficiency. So we will have also the session for this scaling up. Yeah, the development of flexible perovskite solar cells will be definitely needed for the future applications, so that it can evolve toward stretchable and wearable applications ultimately. And yeah, I also would like to introduce a little bit of perovskite LEDs. So yeah, perovskite can be used and also used as a light emitter, as you know. So it is based on these materials properties that we discussed. So then why is perovskite good in LEDs? So now actually display technology is currently inseparable from our daily life, and people seek to see more vivid and realistic displays. So in this sense, perovskites have a great potential and advantage as a next generation light emitter, because perovskite have high color purity with a very narrow full width half maximum FWHM of electroluminescence EL spectrum. So this is much narrower than that of the other light emitting material and the LED devices. And in addition, perovskites have advantages such as color tunability, and also what I already mentioned in the solar cell part, high charge carrier mobility, high defect tolerance, etc. The charge carriers do not have to go through very harsh condition where they end up with combining non-radiatively, but the injected charge carriers can emit the light by a radiative recombination efficiently. So yeah, based on these advantages, perovskite LEDs have achieved efficiency over 20%. I mean, this is different from power conversion efficiency, but external quantum efficiency in very short term, less than several years, like perovskite solar cells. So perovskite, as we discussed, which includes both organic and inorganic components, this can take advantages from each. So optoelectronic properties of this perovskite is really good. One another attractive point perovskite as a light emitter is, I just briefly mentioned the color tunability. We can simply tune the emission color by compositional engineering. More simply saying, by halide substitution. So as you can see here, by substituting iodide with bromide or chloride, the results in the blue shift light emission here is the same as increasing X. Iodide decreases and bromide increases, then we see the blue shift of the observance, and the film color changes as well. So this indicates that the halide substitution changes the band gap from iodide to chloride. The band gap widens, so we see this blue shift. The band gap narrowing or widening is associated with this electronic state, electronic structure again of lead halide, as we discussed before. So the use of bromide or chloride will drag down this orbiter compared to when we used iodide. So we have like a wider band gap and a blue shift. So the use of perovskite emitters can realize various color emission as you wish, and this can achieve the technical accomplishment of white perovskite LEDs ultimately, either based on RGB system or a tandem structure. But here we have a similar problem to the one we discussed in perovskite solar cells, stability. So yeah, despite this evolution of efficiency, the operational stability of perovskite LED is even worse. So the longest operational stability reported of this perovskite LED is about several hundred hours here for green, and it's much shorter for red, and blue diodes are like very short. Yeah, so considering the other display applications lasting at least like hundreds of thousands of hours, perovskite cannot be used for practical use in this stage. But yeah, I believe there will be a point where this stability issue of the perovskite optoelectronic devices, including solar cells and LEDs, can be overcome and finally commercialized. So yeah, this is all I prepared. Did I finish a little early? Yeah, thank you for your attention, and if you have any questions, please.
Okay, thank you very much, Dr. Homion, for this nice introduction and nice travel around the perovskite. I think that we have just one question here in the chat that maybe you already answered during the presentation, but I'm just going to read it. So we have the question that why do perovskite degrade so fast, 20% or more in the 5th year? I know it's a very complicated question, but please, can you give just a small answer about it?
Sure. Actually, yeah, as I said, it's from the basically the structure of perovskite based on the ionic bond. So it's weak and it's inevitable to have ionic defects. So for example, you know, let me bring an example to degrade the efficiency or stability very fast. So we operate the devices, right? And then we constantly have the electric field in a device. For example, solar cell, it has like, if you maintain like maximum power point, then some less than 1 volt. For LEDs, it will be much greater than 1 volt, like 4 volts. And then, according to the field, electric field across the device, there will be much faster or like ion migration, and then the accumulation of these ions at the interface, which can degrade the interface very fast, which accelerate the device degradation again. So it can be like one of the critical problems that leads to the degradation during the operation of devices. Yeah.
Okay, thank you very much, Javier, for your answer. We have a couple of questions more here. So which structure yield better efficiency as well as stability, planar or mesoscopic?
I cannot judge by myself, but according to literature so far, so having this mesoporous structure seems more stable in terms of stability. For example, it is known in general, planar heterojunction perovskite solar cells are more susceptible to this ion migration things. So probably the flattened interface maybe there would be like several parameters that we have to consider. But yeah, so far I can say the mesoscopic structure so far is more stable than the planar structure cells.
Okay, thank you, Javier. Third question, it's about opinion about lead. Do you think it will be a legal health environmental problem? Do you see future lead-free perovskite devices? I think that maybe this question is going to be also part of the next talk about sustainability, but please, Javier, you can say your opinion about it.
Sure. Yeah. Definitely there will be a separate session to deal with this kind of sustainability and environmental friendly things. In my opinion, lead here would not be very serious. This is my personal opinion, considering the regulations and limitations and laws in many countries. Actually, the amount of lead inside perovskite material and cells, even in modules, even in large scales, will not be very significant compared to like batteries or that we everyday use in car or wherever. So I have to look through everything. But as far as I know, it does not exceed like so much the level of regulations in many countries. But still, of course, the best will be annihilating lead totally in the perovskite solar cell. That will be much more environmentally friendly. That would be our ultimate goal, one of our ultimate goals in this field. Yeah.
Thank you, Javier. And the last question, can you please expand a little bit on the passivation technique via 2D perovskite?
Yes, sorry, what was the question again?
The student asks that if you can please expand a little bit on passivation techniques via 2D perovskite layers.
Technically, how we, so there will be like some different approaches, but basically the most common approach is to deposit 2D perovskite on top of 3D perovskite, like this layer by layer kind of. so that we can cover this the underlying, we can protect this underlying 3D perovskite from like external stresses, like as I mentioned, the moisture, or mostly moisture, and some metal ion ion migrations as well. The other approach is to incorporate this 2D perovskite in this bulk, so that we have, I think we see this grain boundaries is filled with 2D perovskite here, for example. Yeah, this is the right example that I just like to introduce. So in this case, you could mix in the precursor solution with this 3D perovskite solution. Partly, if you put a more like too much amount of this precursor to make a 2D perovskite, the efficiency will, and the stability even, will be very bad. So the control, the amount of control of the amount of 2D perovskite precursor would be key. And or you could just like make a low dimensional perovskite rather than 3D, 2D type. Then you're gonna lose some efficiency, but you're gonna get some stability, because 2D perovskite is more stable than 3D perovskite.
Okay, then finally, I'm very excited to see all the interest in your talk, Javier. Finally, I have one question. What is the main reason behind the high defect tolerance in perovskites?
Tolerance fact, I mean the high defect tolerance. I'm sorry, because I cannot read the question by myself.
Yeah, it's the main reason behind the high defect tolerance. Maybe the person who wrote this question can be a little bit more specific about it.
So the main reason of this high tolerance, high defect tolerance of perovskite is so there are like as far as I know, I mean, I have to look through it again, but this is because of this lead, strong spin orbit coupling of lead, this heavy atom inside. It somehow, by interacting with these halides, these, for example, the state, the trap states or orbiters can be repelled from this band gap. If you have like states in between here, for example, we call it like a deep level trap, which is very detrimental to device performance. But we also have like shallow traps close to these band edges. This kind of shallow traps can be just repelled. I mean, not very significant because of a strong spin orbit coupling of lead ion under the condition of this direct band gap. So this is my answer. It would be very complicated if you go deep inside this physics, but yeah. I'm not sure if this answer was enough.
Okay, Javier, thank you very much. I think that you're right. It's very complicated to go deep in some aspects of the technology, since it's a complex technology, not only from the commercial point of view or the application point of view, also the physical-chemical phenomena inside this technology it's complicated, and it's very wide. So maybe if people have interest in continue with questions or doubts about Dr. Hobden talk, can contact him directly, and of course he can answer the questions with more in depth. Okay.
Sure. Yeah.
Thank you very much, Fabian. And we need to have a small break. I think we are on time. So we are going to start again in 50 minutes. So thank you very much, and we see you in very soon.
Thank you.
Can you hear me now? Okay, just some technical information before to restart again. Remember that at the end of the day we will have the quiz. You will have a link to a Google Forms. Remember that you have only half an hour from 4:30 until 5 o'clock. And if some issue happens that the Zoom is not working or it's disconnecting, remember that you have to connect at the same link, always the same link. That's it. If you have some questions, remember you have the chat. You can ask some questions to the speakers using the questions and answers from the bottom of the screen. And if you have to enter room, just you can use the chat. So thank you very much, Anna. It's your turn.
Okay, thank you, Joan. So we are going to start with the second session of the day dedicated to modeling. Thanks to the two panelists that we have today, Dr. Uli Werfel and Dr. Antonio Guerrero. So we are going to start with Dr. Uli Werfel, department leader and lecturer from the Fraunhofer Institute for Solar Energy System, Fraunhofer ISE, and Freiburg Material Research Center of the University of Freiburg. His research interests focus principally on the fundamental analysis of the working principles of solar cells, charge carrier selectivity in optoelectronic devices, optoelectronic characterization of numerical simulation of solar cells, as well as upscaling of low-cost photovoltaics with a short energy payback time. He is author of about more than 100 peer-reviewed research papers and a book about the physics of solar cells. He gives 3 lectures of different aspects in photovoltaics at the University of Freiburg. In the next talk, in charge of Dr. Uli, he will introduce the effects that originate from the presence of mobile ions as an example of these diffusion simulations of perovskite solar cells. And he will show how they modify the interfacial recombination and how that affects to the electrical output of the solar cells. A comparison between experimental data will be drawn during his talk. So, Dr. Uli, the floor is yours. Thank you very much for being here.
Thank you very much, Anna, the organizers. I will share my screen. Yeah, good afternoon, everybody. I will share some results about modeling. As I don't know you, it was of course hard for me to decide what to show and what not. So I think I must fail, but anyway, I tried my best. So before we go into the results, I want to introduce certain aspects. Just to remind you, I guess some of you know this, others may not. Any kind of solar cell has these different units. It's sandwiched, let's say, between electrodes. Usually the front electrode is as transparent as possible to let the light shine in. Usually the backside is reflective if you don't want to have a see-through element. And in between we have different units, which we call transport unit, for example, for electrons, an absorption unit, and a transport unit for holes. These 3 units are not necessarily from different materials. If you think of a PN junction crystalline silicon solar cell, for example, they are all from the same material, but there might be different degrees of doping. But if you look at a perovskite solar cell or organic solar cell, other type of solar cells, they are rather made of heterojunctions, so an absorption material, in our case it will be the perovskite absorber, sandwiched between different materials, which are, let's say, good in exchanging only one type of charge carrier with the absorber. Yeah, we will come later to this point again. I show you some experimental results, and I thought it's good maybe that you just get a small overview of how they were made. It's based on a glass substrate with indium tin oxide, and then we use different hole transport layers, hole transport materials, which exchange or extract holes from the photoactive absorber, which is here a mixed cation mixed halide perovskite as the central absorber unit, and then we have also two different electron transport layers, which extract electrons from the absorber and finished by aluminum top contact. Yeah, all these layers are deposited at low temperatures and under ambient air, except for the electrodes. When we measured those solar cells, after they had been in the glove box for 2 or 3 days, we saw something that was very surprising for us. Yeah, here you can see on a time scale of several hundred seconds, you can see the open circuit voltage. This is the black line. And at the same time, we measured the photoluminescence intensity. This is the red line. And this is something which you would not expect like this, because in a solar cell, usually the open circuit voltage and the photoluminescence intensity, they are somehow very strongly linked to each other. The reason being that the open circuit voltage usually tells you how many charge carriers you have in your device. If you have more charge carriers, you have a higher open circuit voltage. If you have less, then have you a lower. If you have a higher charge carrier concentration, or if you have a high charge carrier concentration, it means that you will also have a high photoluminescence intensity, because the photoluminescence which you observe with a detector, with a camera, is the product of radiative recombination, and that itself is just proportional to the product of electron and hole density. So somehow we observe here two strange things. First of all, the open circuit voltage starts at a really low value, but then over, let's say, some hundreds of seconds, reaches a good value of close to 1.1 volt. For these kind of solar cells, it was a good value. And second, there seems to be decoupling, because the photoluminescence rises very steeply in the beginning, but then stays constant. And the dashed lines, they tell you what you would expect if you apply the usual theory. So if we take the black line as, let's say, the given result, then we can calculate what kind of photoluminescence intensity would we expect if everything would be normal. And this is the dashed red line. And you can see it's very different from the one which we actually measured. You can do the same also the other way around. You take the PL signal as the input result and calculate from that the open circuit voltage which you would expect. And this is shown here in the black dashed line. Yeah, so we can see something is not normal here. Yeah, it's very, let's say, puzzling result. Interesting is, of course, also that the solar cell that behaves, let's say, very bad recovers quite well under illumination and open circuit conditions. But yeah, what let's say most caught us is this obvious decoupling between the photoluminescence intensity and the open circuit voltage. We also measured the normal current voltage characteristic. I'm sure you have seen such a curve in the morning maybe, before and after light soaking. And as you can see, the current is very much the same, but you can see, of course, the much higher open circuit voltage after some minutes or whatever of light soaking. Okay, before we explain these results and shine light on what the role of mobile ionic species in perovskite could be, we go back to, now comes the boring part, I'm sorry. This is the current voltage characteristic, which you can, if you want, write like this. So now we have a one-dimensional problem. We are only interested in the direction perpendicular to the plane of the electrodes. Yeah? And we can say that the current or current density as a function of voltage is given by recombination minus generation. Yeah? And you have to take into account that once generated, charge carriers that survive recombination exit the solar cell as an electrical current. Yeah? There is no third possibility. So if you operate your solar cell, for example, at the maximum power point, and you generate charge carriers, they can only either recombine or exit the solar cell and contribute to the electrical current. There's no third possibility. Usually, the generation rate is not dependent on the voltage. It's just dependent on the position where you are in your device. Whereas the recombination depends, of course, strongly on the voltage. Yeah, it's the recombination that is responsible for this exponential rise in forward direction of a diode. Yeah, you may all know this. And now we have to think about what makes electrons and holes move in an absorber, in a semiconductor, in a solar cell. Yeah? If we want to have an electrical current, we need to have electrons and holes moving in different directions, because if they move to the same direction, then we have individual particle currents, but we don't have an overall electrical current. So in order to have an electrical current, we need to have something in the solar cell that makes sure that electrons go to one side, in this example to the left side, and holes to the right side. What are driving forces for electrons and holes to move and finally, let's say, make a current to be measured? In this example here, this is a band diagram of a semiconductor. You can see the electrical potential energy of an electron. This is minus the elementary charge times the electrical potential. Yeah? And you can see that there's a gradient. It's not constant over the spatial position. The band edges go along with the electrical potential energy. Yeah? They have the same inclination. And what you can see here in this example is that you have a driving force, which is the electric field or the gradient of the electrical potential, but you don't have any chemical potential difference. This can be seen by the difference between the quasi-Fermi level and the conduction band, or the quasi-Fermi level of the valence band and the valence band. Yeah. So if we look what we usually do at one single material, for example, the absorber in a solar cell, then the chemical potential finally, let's say, what we have to take into account is the concentration of charge carriers. So this picture here means that the concentration of charge carriers is constant. It's the same everywhere. So there's no reason for diffusion, yeah, for macroscopic diffusion. Of course, the charge carriers are bouncing around, yeah, due to the thermal energy, but there's no directed movement due to concentration differences. We have all the same concentration everywhere. So in this case, the current will only be driven by the electric field. Then, of course, another example, we have no electric field. You can see that the electrical potential energy is constant over the spatial position. But now we have a strongly differing concentration of charge carriers. We have many charge carriers here on the left side and few charge carriers on the right side. So that will cause a diffusion of charge carriers from the left to the right. Okay. The nice thing is we can combine these two. Yeah? In principle, the equation reads like this. An electrical current density of a particle I is given by minus its electrical conductivity divided through the number of elementary charges. For an electron, the Zi is -1, for a hole is +1. In terms of ions, it can also be +2 or so. Yeah? And then you have the gradient of the chemical potential and the gradient of the potential electric energy. And these are both energies. The chemical potential has the unit energy. Unfortunately, we always speak of an electrical potential and it does not have the unit energy. Yeah? But the electrical potential energy is an energy. Okay, so we take this one, the gradient of these two. Now, mathematically, of course, gradient from A plus gradient from B, you can also make the sum first and take from that the gradient. And this two, so the chemical potential and the electrical potential energy, can be put together and we call it electrochemical potential. Yeah. And the good thing about it is that the gradient of the electrochemical potential is the total force. Yeah. So we have two properties of electrons and holes were relevant properties. Of course, electrons could also react to magnetism or gravitation or whatever, but temperature differences, this is not relevant in a solar cell. So in a solar cell, it's diffusion, chemical potential gradient, and electric field, yeah, what makes charge carriers move. The nice thing, if you combine it like this, is that you then only have one force, yeah? You have only to see, is there a gradient in the electrochemical potential? If yes, particles move. If not, they don't move. An example that, let's say, is a little bit similar is when you look at the atmosphere, yeah? The gas molecules, the air. If the atmosphere were isothermic, I know it's not, but let's just assume it for a moment, then we would have an exponential distribution of charge carriers. Sorry, not of charge carriers, of gas molecules. Yeah? We would have a lot of them down near the surface of the Earth. And then if you go up, you know it maybe if you were already at a height of whatever, 3, 4, 5, or even 6,000 meters, there's less air. Yeah? And if it were isothermic, everywhere the same temperature, then this decrease would be exactly exponential. The combined potential, what we have to look at in the atmosphere, is the gravitochemical potential, because the gas molecules are subjected to gravitation. Gravitation would take them down to Earth and then they would stay there forever. But chemical potential tries, so to say, to distribute them evenly. Yeah? So if you have a lot of down on Earth, there will be a diffusion trying to distribute them more homogeneously. And what you can nicely do there is as well, you can first add up the driving forces or the potentials, and then the gradient, in this case of the gravitochemical potential, would tell you if there is, let's say, a movement or not, a macroscopic movement or not. Yeah? So this is an example which is similar to this. We sum up the two driving forces and we call the resulting driving force electromagnetic potential. I have not the time to really deduce this, but I hope you believe me anyway. In a solar cell, you can show that these electrochemical potentials of electrons and holes are equal to the quasi-Fermi levels. There's a quasi-Fermi level of the conduction band, which is an energy level that describes how many electrons you have in the conduction band. And this is the electrochemical potential of the electrons in the conduction band. And for holes, the quasi-Fermi level of the valence band, so an energy level which describes how many states are occupied in the valence band, is minus the electrochemical potential of the holes. And then if we rewrite this equation, then an electrical current density is given by the conductivity of electrons divided by the elementary charge times the gradient of this quasi-Fermi level, and the same for the holes with the Fermi level, quasi-Fermi level of the valence band. That this is advantageous to do like this, you can see in the following slide. This is a situation which is somehow strange because we have an electric field, but at the same time, we also have a chemical potential gradient. Both would generate currents or drive currents. But you can also see, in this case, there's only a single Fermi level. So this would be a semiconductor in the dark, for example, without applied voltage. There is no gradient in the electrochemical potential. So we have individual gradients, both of potential electric energy and chemical potential, but no gradient of the sum of the two. The result here is no current. It's not that there are two currents flowing, because can that be with two driving forces acting on the same particle? It's like, imagine you sit on a chair, there's some wheels on the bottom, and somebody pulls your right arm to the right, of course you move to the right. But if with the same force somebody pulls your left arm to the left, then maybe it will ache after a while, but you won't move anywhere because the resulting force acting on your body is zero. This is the same here in this situation. Yeah? If the driving force for, let's say, diffusion and the driving force for migration, electric field, is the same but in opposite direction, then they sum up to zero and we don't have any current. Yeah? You can't measure a current of a PN junction in the dark. And there you have exactly this, this situation. The bands look then a little bit different, but you have both an electric field and a chemical potential gradient, but there's no current flow. Okay, so it's advantageous, as I think, to look at the overall driving force, see if this is different from zero, and then this will drive current. All right, so now we have spoken about the transport of electrons and holes and about the current, which is given by the difference between recombination and generation. And of course, for modeling, I mean, the computer does it. Yeah, we don't have really to take care of it, but of course, there's also a Laplace equation. Yeah, that the second derivative of the electric potential is a function of the space charge density. Yeah, so if you have somewhere a volume where you have more electrons than holes, then this creates an electric field. Yeah, as you, I guess, well know. Okay, so in the modeling, what we do is, I mean, nowadays we use usually computer programs, yeah, that are able to, or you also have to, let's say, control it, that the computer does it in a good way. You cut your device in many, many small pieces, yeah, so discretize it, and then the computer solves these different differential equations for the density of electrons and holes, and let's say lets these driving forces act on these particles, and takes into account that it's self-consistent in the way that the result is always satisfying also this Poisson equation. Yeah? So what the computer then does is, as usually these differential equations are cannot be solved analytically. Yeah? So there's not a real solution which you can write down. So the computer guesses a solution and then recontrols it or checks it, whether, let's say, it satisfies certain conditions of accuracy. Yeah. And if not, then what he can do, let's say very nicely, is then he does a small variation in a certain direction and sees if the result is getting better or worse. Yeah, and this way he finally finds a solution which is well, let's say, in this boundary condition of accuracy, and then he goes on. Yeah, so this is the way it goes. But come back to solar cells. What else do we have to take into account? Well, we have to take into account different recombination mechanisms. Radiative recombination is usually not the dominant recombination mechanisms in real solar cell, but the nice thing about radiative recombination is you can see it, maybe not with your eyes, but with a detector. Yeah. So this is really a big advantage of this type of recombination. So although it might be small, if you have the right detector, you can observe it. And you know it's proportional to the product of the charge carrier densities. Yeah, so it tells you a lot about, let's say, the inner life of the solar cell. The other type of recombination, where I will not go into detail now, Auger recombination, impurity recombination, but maybe 2-3 words about surface recombination, because this will play a role in the following. Surface recombination, if you have a semiconductor absorber, it has to end somewhere. Yeah. And if it ends, for example, there is no metal or other layer on top of this, still then you have, of course, an abrupt stop of the periodicity. Yeah? So inside the crystalline absorber, you have this very periodic arrangement of atoms atoms. And then at the surface, it suddenly stops. And this gives rise that there are some unsaturated bonds and so on, and they create states for electrons and holes within the band gap, which you can see here. Yeah, so in a very super clean, perfect crystal, you would only have states in the bands, here conduction band, down here valence band, and in between you have the band gap and no state which is available for electrons. Yeah, so it cannot be occupied. But at the surface you have that, and this means that if an electron arrives here, it can go down step by step by step by step by step. At each step, it loses a bit of its energy. Yeah, this goes into lattice vibration, so finally heat, and finally it arrives down here at the valence band, and then the recombination process is complete. So you don't have any neighboring atoms at the surface, and also many times you have some impurity molecules which are either physi or chemi adsorbed at the surface, and they create these additional states within the band gap. Somewhere we have, however, to put a metal, right? If we want to collect our current, we sooner or later have contacted with a metal because we need high conductivity. Yeah? If you collect, if you have a very good solar cell, it will deliver a lot of current. If you make it larger, it's more current. So sooner or later, you need metal to collect these charge carriers. Otherwise, you have the voltage drops, the ohmic resistance is just too high. Yeah? At metal surfaces, it's extremely or especially problematic. The reason being that if you look at the metal has a Fermi level, which means that more or less all states until this Fermi level occupied, and towards higher energies, nearly all states are empty. And let's say usually any kind of metal, you will see that an electron in the conduction band of the absorber is above the Fermi level of the contact, and the hole in the valence band is beneath it. So an electron will always find an unoccupied state energetically, and from there it can go down quickly to the Fermi level. And the same with a hole, which is an unoccupied state. Okay. So in other words, we can say that at a metal surface, if an electron and a hole arrive there, they are lost. No chance. Yeah. This is now, of course, an extreme case where you can also see you appear the quasi-Fermi levels. Remember, these are the electrochemical potentials. So a gradient in this is the driving force. Here you can see that you have a bending, so you have a gradient in the quasi-Fermi levels. This drives electrons and holes to the same surface. Yeah? So you don't have necessarily an electrical current, but you have at the same time an electron current and a hole current, summing up to overall 0. But it means that you lose charge carriers there. Yeah. So this is especially problematic because we know we have to put metals somewhere, but at the same time, at least if both charge carriers arrive at the surface of the metal, they are lost by recombination. This is unavoidable. Good. This brings me to more consideration about the requirements for electrodes and solar cells. Of course, electrodes have optical and electrical properties, like, for example, conductivity and transparency, reflectivity, which have to be very good, but these can be determined rather easily. But the selectivity, like, for example, putting some metal here, how does this increase or decrease the rate of electrons and holes which are lost by surface recombination? This is usually not known. Yeah? It's harder to measure. You cannot measure it directly. Okay, if you look at it from a very general point of view, this is again an absorber with a conduction and a valence band, then an ideal selectivity of a contact means, for example here, that this contact exchanges only electrons with the conduction band of the absorber and no holes with a valence band. This would be ideal selectivity. It's like a semi-permeable membrane. Yeah, here, only electrons are exchanged in both directions. The solar cell, you want more to extract the charge carriers. In an LED, you want more to inject the charge carriers. But as you know, a good solar cell can also operate as an LED. Yeah? And for the hole contact, we need it to be vice versa. We need a good exchange with a valence band, so holes are exchanged here, and no electrons in the conduction band. Then if we realize this, then we have no surface recombination at the electrode absorber interface, and we achieve the maximum open circuit voltage for this particular absorber. It's not necessarily the overall limit, which is called Shockley-Queisser limit. This is when electrons and holes can only recombine radiatively. Yeah? But I mean, you have maybe some impurities here, but it's the best what you can achieve with your absorber. It means that putting the electrodes on the absorber does at least not lead to additional surface recombination. Now the question is, how do we make sure this? Because I just told you that if holes and electrons arrive at the metal surface, they're lost. Then you already can see, okay, we have to prevent already before that the wrong type of charge carrier arrives at the surface. How do we do that? Again, from a fundamental point of view, you find that what you need here in front of, let's say, the electron contact, you need something, yeah, a material, whatever, that makes sure that you have a very low conductivity of holes and at the same time a high conductivity of the electrons. Yeah? Very simply spoken, if the conductivity of holes is very low, they can't go there. Yeah? Very important is that this condition has to be maintained under operations for illumination and voltage. And for the hole contact, it's just the other way around. Why is this so? And sorry, the electrical conductivity is elementary charge times mobility of either electron or hole times the charge carrier concentration. Maybe a short question to Anna or somebody. I see only my own presentation. Are there questions? Would I see if there are questions? Or will there be, let's say, questions only in the end?
Normally we are doing the questions at the end of the talk, Uri.
Okay, good. Then I will just go on. No problem. Okay. So why is this so? Here you can see a band diagram, which is now without band bending. It's just a scheme for a solar cell under open circuit conditions. You can see the conduction band, the valence band. You can see the quasi-Fermi level of the conduction band and of the valence band. Usually at the contact itself, at the metal, we only have one Fermi level. Yeah, inside the metal, we cannot have two different Fermi levels. So the two quasi-Fermi levels have to merge at the surface. And if everything goes well, then this is straight. Yeah, for the electron contact, the quasi-Fermi level of the conduction band is straight. So the other one has to be very steep here, yeah? And vice versa at the whole contact. But I don't know how familiar you are with this graphics, but this here constitutes a large driving force. Yeah, I told you the quasi-Fermi level of the valence band is the electrochemical potential or minus the electrochemical potential of the hole. So if this is going up, it means that this is energetically going down electrochemically for the hole. So they have a large driving force towards that surface. And the same here for electrons. So then you can say, this is really bad. How can we circumvent this? Actually not, because the separation of the quasi-Fermi levels here inside is more or less the open circuit voltage or the voltage of your solar cell, and you want the voltage to be large. Yeah, this is very, very essential. Yeah, we want to maximize the voltage of our solar cells because this then also maximizes the electrical power which they deliver. So we have to live with this problem. Yeah, the better, even more, the better our solar cell in terms of voltage, the higher we have a driving force in the wrong direction. Yeah, for holes close to the electron contact, they will be driven to the electron contact. We cannot avoid this. So this is of course a problem, but how can we nevertheless reduce the losses there? If we look at the equation, yeah, you have two components that rule how much or how high, how large your current is. The driving force we have already discussed. And here you can see that the driving force for the holes is there. It will be there. Yeah, if you have voltage, it will be there. But you can see that it's a product. There's the conductivity, the electrical conductivity is also there. Now you can see we have to manipulate the conductivities. Yeah. So these guys we have to engineer, whatever, manipulate in order to make sure that although there is a large driving force, holes will not go there. Yeah, this is the art of making a solar cell. I know that this is now only theory. In real experiments, you have many other conditions that you have somehow to satisfy. But this is really an art of making a solar cell that you make sure by the arrangement of the materials and the nature of the materials that the wrong type of charge carrier can't go towards the wrong electrode, let's say, although there is a large driving force. Okay. So this is why I just repeat the slide, why we came up from a very fundamental point of view with these conditions. Yeah, you need something close to the electron contact, which makes sure that you have a very low conductivity of the so-called minority carriers, of the carriers that you don't want to have there. All right, now coming to the simulations and the results. So this is a scheme of how this is then simulated actually. So We tell the computer we have an absorber. The absorber has a certain thickness. It has a certain band gap. It has a certain density of states. The charge pairs have a certain mobility. The overall device has a certain temperature. All this is, of course, given as parameters. And then between the absorber and the electrode itself, the contact, we insert wide band gap N and P dope layers. Yeah? These represent the famous electron and hole transport layers, where there's a large variety in experiments with, especially with perovskite solar cells. Yeah, people try to optimize it more and more, but we already have quite a number of different materials that we can use there. Yeah, for example, on the hole contact side, this blue material here could be nickel oxide, it could be PTAA. Yeah, there are many different possibilities. And for the N side, could be tin oxide, could be titanium oxide, it could be PCVM, an organic semiconductor. Yeah? So there are many choices there. Okay, now let's look again at this result. So we want to understand why is this happening. And in order to, we had an idea of what for sure has to be going on in this device, that you can have such an extreme decoupling of the PL intensity and the open circuit voltage. Again, I remind you, the red solid curve is the measured PL intensity. And if we derive straightforward from the theory, the open circuit voltage that we would expect from this, we end up with a dashed black line. And you can see in the end, of course, yes, they are the same, but here, yeah, during the first 200–300 seconds, the open circuit voltage is so much lower, yeah. And we thought about it, what could be the reason? The high PL intensity means you have already here, at this point in time, you have a high charge carrier density, but somehow the high charge carrier density does not translate into a high VOC. Why is this so? Here you have 3 different cases. Please look first here at the left. This is a good solar cell. It has a large separation of quasi-Fermi levels within the absorber, and the quasi-Fermi levels of the majority, so electrons here and holes here, go straight, and then the elementary charge times VOC is the same as the quasi-Fermi level separation. So this is, let's say, what you want to achieve. Yeah? This device would then also have a high photoluminescence intensity, and its PL intensity correlates directly with the open circuit voltage. You could have a problem with the surface and lose a lot of charge pairs by an additional recombination mechanism, which in principle is avoidable. For example, you choose very bad electron and hole transport materials, yeah, which are not very well suited. Then you have a lot of surface recombination. These charge pairs, which recombine at the surface, cannot recombine radiatively in the volume. And due to this additional loss mechanism, you decrease your charge carrier concentrations. Yeah? It's like, imagine this is a cup. I pour in water, this is the generation rate. I have a small hole here where the water pours out again, but of course, at a certain filling level. This is the steady state, the equilibrium situation. Yeah, I pour constantly at a constant rate some water inside, and the water is going out here at a certain filling level. Now imagine I drill another hole. What will happen? Again, after some time, I reach a steady state condition because I'm pouring still the same amount of water, which symbolizes the generation of charge carriers. But now, due to the second hole, the filling level will decrease and the new equilibrium will be reached. So again, per time unit, the same, what is going in is going out, but now I have the 2 holes, so the filling level will be lower. Yeah, this is exactly what you can see here in the middle. You have an additional loss mechanism. It leads to a decrease of charge pair concentration, and therefore quasi-Fermi level separation, and you will measure a lower open circuit voltage. But still, the PL intensity, which is then also lower, will still be correlated to the open circuit voltage. Now, again, we have seen a more or less high PL intensity, but a low VOC at the same time. And there's only one possibility how this can happen. And this is depicted in this picture. In this picture, we assume that at the hole contact, yeah, it could also be at the electron contact, we assume that there is not only this gradient of the minority carrier quasi-Fermi level, yeah, of the electrons, but also of the holes. Okay, this can happen. And if it's only close to the surface, then you can see what happens. The open circuit voltage is strongly reduced compared to that case here on the very left. But the overall separation of the quasi-Fermi level, I mean, throughout the device, is hardly changed. Yeah. So this kind of situation would give rise to a low VOC and at the same time a high PL intensity. Yeah, I hope you get the point. Yeah, there is no other possibility, because if the gradient would already start, you know, from very inside, from the other side of the absorber, then the separation of the quasi-Fermi levels could not be that large. Yeah, so here only this kind of, I mean, could also be on the other side. Yeah, this we don't know, but at least on one side we have this situation where a part of the voltage is consumed due to a gradient in the majority carrier quasi-Fermi level, in this case the holes, but we still have an overall high charge carrier concentration in our absorber, therefore a high photoluminescence intensity. Okay, now this was in our mind, and then of course if you think about perovskite and then you have transient effects on the let's say the 100th of second time scale, then thinking of mobile ionic species is kind of, yeah, obvious. Okay, so we thought, aha, maybe we try to simulate perovskite solar cells, including mobile ionic species, and see whether we can reproduce such an effect. This is what we did. So we told the computer, in addition to electrons and holes, there are ionic species, and we arbitrarily assumed that the positive, in total it's of course neutral, yeah? So we could not just implement one type of ionic species, we also needed the countercharge. And we said, okay, the positive charges, they are fixed, they can't move. And the negative charges, these are not electrons now, these are ionic species, these are mobile. Okay. Now, I guess most of you know that in a solar cell, if you have different contact materials, being it metals or electron hole transport materials with different Fermi levels in the beginning, yeah, then they give rise to built-in voltage. Yeah? The built-in voltage is also what you have at the PN junction, this total amount of band bending. Yeah? This is the built-in, so-called built-in potential difference of built-in voltage. As we have a built-in voltage in a perovskite solar cell, so in this case, the electron contact is on the right side, the hole contact is on the left side, and then we have an electric field, a built-in electric field, which goes from right to the left. For this reason, the electron contact, this is the let's say the material which injects electrons into the absorber, because it has a higher Fermi level in the beginning, is positively charged at its surface. Therefore, the negative charge is also, let's say, the same. In other words, there is this built-in field, yeah, and therefore these mobile ionic charges, which are negatively charged, are now going towards the electron contact. And here, close to the hole contact, which is made as being not so good, yeah, you are left with this fixed, spatially fixed positive charges, because the mobile negative charges have gone from the left to the right. Now, of course, you can easily think that because now here we have excess positive charge, holes will be repelled from that region and electrons will be attracted. Yeah. So what we get here close to this hole contact, due to the distribution of the ionic species, we get a rather high concentration of electrons and therefore a high electrical conductivity of electrons. Yeah, it's proportional to each other. And at the same time, a rather low hole conductivity, because holes are repelled by this positive charge here. Now, if we now light soak, or which I didn't mention, forward bias our device, yeah, we switch on the light, we keep the solar cell under open circuit condition, like in the experiment I showed you, where you saw the transient rise of the open circuit voltage. then due to the build-up of electrons and holes, the built-in voltage is weakened. Yeah, it's reduced. It can even flip to the other side. That depends, of course, on the exact parameters. But for sure, the built-in voltage which you have in the beginning is somehow getting smaller. Now, this then leads to the situation that these negative ionic species would rather go back to this side. If they do, then we have here more or less a neutral situation, or even maybe some excess negative mobile species. This is good because now we have a low conductivity for electrons. Yeah, they're not attracted, they're repelled by these negative charges, and we have a rather high electrical conductivity of holes. And if you remember back what I said, in order to prevent electrons, in this case the minority carriers, we don't want electrons to go to the hole contact. A low conductivity of electrons helps, yeah, because electrons usually don't go there where the electronic conductivity is very low. Yeah, they go the way of the least resistance, so they can go this way and that way, but this way is with a high conductivity, and this is with a low conductivity. Most of the electrons will go the way with a high conductivity. Yeah, I think you know this if you have, for example, two resistances in parallel. One is very small, one is big. The current will flow over the small resistance, yeah, or most of it. Same here. So what I can say is the implementation of mobile ionic species led to the fact that the presence of these mobile ionic species changes the built-in voltage, the electrical potential distribution, and this has an impact on the distribution of electrons and holes. And as we have learned before, the distribution of electrons and holes, and especially their conductivity, is ruling finally if you have a lot or not so much surface recombination. So first of all, and we call this unconditioned, and then after light soaking, you know, when the open circuit voltage is high, we call it conditioned device. First of all, we started with an homogeneous distribution of both kind of ionic species. It was not looking like this in the beginning, but we told the computer, yeah, that evenly distributed positive and negative charges. The positive keep their place, they're fixed, and the negative can move. And here you can see that in the unconditioned device, the ionic density is here peaking, yeah, of the mobile species here in front of the electron contact, and there is nearly nothing going on near the hole contact. But after the light soaking under open circuit condition, this conditioned device then has the ionic species just the other way around. Yeah, they peak here at this close to the hole contact, and we have very few at the electron contact interface. Yeah, so there you can see exactly in numbers what I try to explain here with the schemes. Yeah, here you can see it in real curves. Okay, and then this is again the experiment, and this is the simulation. Yeah, so we managed to reproduce these results quite accurately. And the nice thing is, of course, then in contrast to the experiment now with the simulation, well, the bad thing about the simulation is it's not real. Yeah? It's a model, you assume certain things, you set certain parameters to certain values and so on. Yeah, it's not real. But of course, you try to pick the parameters as good as you can from measurements that are published in literature or maybe done by your own group. Yeah, so it's not totally arbitrary, but of course, we don't know exactly how the density of states in such a perovskite looks like, and we don't know the exact value of the mobility and so on. But you try, of course, to come close to pick the values the most reasonable manner you can. But yeah, the disadvantage, of course, a model is never the reality. It can only, let's say, describe well certain aspects of the reality. But then there's also a strong point. Once you have come up with a model and it delivers reasonable results, you can access all the information, yeah, which you can't do in experiments. So here, for example, we can ask the computer, okay, tell me the distribution of the ions. tell me the distribution of electrons and holes, and tell me where do hole currents flow and electron currents flow, and so on. So you have access to the complete information, and from this you can learn more, because you can check whether the way you think about, you imagine the solar cell to work is correct or not, yeah, under, let's say, these boundary conditions. Okay. Then I will give you one more example, what else can be done with transient simulation. It's more about just understanding. So there we have not taken an experimental result and tried to remodel it. There's a lot of information in the slide. We will go through everything step by step. So first of all, what is this? This is transient simulation data, where you can imagine at time 0, we started to switch on the light immediately, yeah? And the solar cell is kept under open circuit condition. But it was in the dark before, yeah? So we switched on the light, and then we see how do certain parameters rise. For example, the open circuit voltage. The open circuit voltage here is the black curve. You can see, I mean, this is the logarithmic time scale, so nothing happens for quite some time. And then we have a rather steep increase of the open circuit voltage. Nothing too special, I would say. But it's interesting when you then look what happens, especially here and before the open circuit voltage begins really to rise, because the time scale where it really rises is rather short. Interestingly, you can see that we have now here assumed impurity recombination, that is also called Shockley-Rittal recombination via impurities in the bulk and at the surface. So it's a more complex model. Yeah, we do not only have radiative recombination, but what you can see here that all 3 different recombination mechanisms, they start here, I mean, at the earliest time at a certain value, rather low, and then they grow, and then they seem to be constant for quite some time before then they finally rise to their final values. Yeah. So here you can see we are in equilibrium. The open circuit voltage, the black curve, is constant. The different recombination mechanisms are constant. That means at this stage, recombination and generation are exactly the same. Yeah? Everything that is generated recombines. Yeah? Okay, so why does it look like this? And why do we have this plateau here? It's kind of strange, because, I mean, if you just think of charge pairs which are generated, they accumulate, they start to recombine. Why should this recombination suddenly stop or be constant, although it has not yet reached its final value? Now, this is maybe a good example what you can learn from these kind of simulations. In order to have an open circuit voltage to measure, you have to recall in your head that, I need an electrical voltage to be measured, yeah, at the contacts. And a solar cell is also a capacitive. Yeah? It has also a capacitive nature. And for a voltage to be measured, you need a displacement current. You need to charge, let's say, the capacitance. Yeah? That is also a solar cell, or solar cell is also a capacitance. Yeah? And this takes some time. You need charge pairs to really separate, and they flow towards the electrodes. Yeah? Either towards until they are at the surface of the electrode or a bit before. I will show you a slide later on. But you need this kind of separation of charge pairs in order to charge your capacitance. And the nice thing is, if you look at this slide here, this is the displacement current, where you can see that during this time where the recombination rates are, let's say, surprisingly so constant, you have a large rise in displacement current. This displacement current means you charge the electrodes, and this gives them rise to the very steep open circuit voltage increase, after which everything is constant, and you can see also displacement current is going back to 0. So this is then the steady state situation where we don't have any displacement current. Yeah? If you go for a very simple model, you can say the temporal evolution of the charge pair density n is given by generation minus recombination. And for the recombination, we can assume in this case just a square behavior. So for example, radiative recombination goes with the charge carrier density squared. Yeah, it's just an example. It's a very simple model. It would then look like this. You shine light, you create charge carriers, you separate your quasi-Fermi levels, and you measure your VOC. Very simple. But this can, of course, not explain what we just saw in the simulation. So to see what happens there, we need to include, in this case, we call it a geometric capacity. It's not necessarily a strictly spoken geometric capacity, but it's very close to it actually, yeah, in real devices. So now the simulation, sorry, not the simulation, the equation is different. We have generation minus recombination, but now we also have to take into account a divergence of the current density, which is a capacitive current, the displacement current density. Yeah. Okay, I will skip over this. You can, of course, under certain assumption, do it that you can solve it analytically. But to tell you from the physics what happens there, imagine you start generating charge carriers in your device. You still have no open circuit voltage because you have not charged your capacitance. Then first of all, now you have more charge carriers in the dark, so you get a separation of quasi-Fermi levels. But if the voltage is still zero, it means that these quasi-Fermi levels here and here are not different. Yeah, they are at the same level. That means if you have a separation, which you need because you have more charge carriers in the dark, then you will have a gradient. Can you see this? This is a kind of geometric outcome of this, that you have more charge carriers in the dark, but you still have no open circuit voltage which you can measure. That means that you have gradients. Now these gradients drive electrons to the right and holes to the left. So, sorry, I forgot to say, yes, we have now the condition that the separation of quasi-Fermi levels in the bulk is larger than the VOC. This gives rise to a current, displacement current. These electrons and holes will charge up the electrodes, and this gives rise to an open circuit voltage, and then you are in equilibrium. And this happens, let's say, during after switching on the light until, let's say, you reach your final state. Okay. The last word on where these charge carriers end up. It's usually, I mean, they are generated everywhere in the bulk, and then electrons move towards the electron contact, which is positively charged at its surface, and holes to the negatively charged hole contact. And with this, you can also see that it will decrease the built-in voltage. It will decrease the built-in potential difference. And whether these electrons end up at the very surface of the electrode or a bit before, this depends on the arrangement of your. Usually, some of them end up on the electrode itself, and some of them end up in a space charge region before the electrode. Yeah? But important is that they are separated, and this takes a bit of time. And when they flow towards the electrodes, they can't, of course, if they flow towards the electrode and arrive there, they are, of course, not recombining. This is why you saw in the transient simulation that the recombination rate reached such a plateau. Yeah, because from then on, many of the charge pairs do actually not recombine, but flow towards the electrons. Okay, so I hope I could show you that numerical modeling of solar cells is very useful, as you can access all the information and you can check whether the hypothesis which you have in your mind is actually valid or not. However, real solar cells are usually much more complex than the model device. You have to simplify. Therefore, my advice would be focus on certain aspects and try to understand the underlying physics as good as you can. Yeah? Because you can never stand there and say, I'm modeling the really complete device. This is, maybe it will be possible someday in the future, but I don't see it right now, yeah? Because it's really, really complicated. So therefore, I think it's better to focus on certain things and make sure that you understand the model. Yeah? And then, of course, based on the simulation results, you could try to think of additional experiments to prove or falsify your hypothesis, yeah? To make it better. Sometimes this happens. You see an effect in experiments. You set up a simulation. You can reproduce it, like the example I showed you, and then from there you go on. Then you say, okay, if this is not true, what kind of additional experiment could I undertake to prove that, let's say, the model is correct? Yeah? And often there are possibilities to measure something in addition. Yeah. Okay, I have still some backup slides, but I think it's enough for the moment. I would like, of course, to thank the European Commission for funding our nice Apollo project, and of course also the organizers of this workshop. And thank you very much for your attention. And I hope we still have some time for questions.
Okay, thank you very much for your very interesting talk, Uli, about I don't have questions here in the chat. I don't know if you are available to answer questions if I write, because we are not on time to have much question now. So if
yes,
you can do it via chat, will be nice.
Okay, I will look into the chat later on. Yeah.
Okay.
Okay.
Thank you very much.
Yeah, you're welcome.
Okay.
Sorry to interrupt, Anna. Dr.
Yes.
Uli, if you can recheck the questions and answers on the bottom of the screen. I think there is a question, and maybe the questions will be there. So please just follow that question, and maybe there you can
I
check.
have not seen a question yet. There's the chat and there's the
on the bottom, on the right of the hand, the yellow hand on the right, there is a box for questions.
Yeah, but there is no question already.
Okay, just to inform you that maybe it will arrive there. Thank you.
Okay. Okay. Yeah. Thank you.
Okay, so let's start with the next talk on charge of Dr. Antonio Guerrero. It's the first invited for this summer out of the consortium of Apolo. So thank you very much, Antonio, to be here and share your knowledge within this summer school. So Dr. Antonio is assistant professor in applied physics at the University of Jaume I in Spain. He is educated in chemistry and completed his PhD in organometallic and polymer chemistry in the United Kingdom. So he joined to the Jaume University in 2010. And over the last few years, his work has been mainly focused in three aspects. One is the Perovskite materials for different applications. The second one, photoelectrochemical cells, and the one, organic photovoltaics. So his contribution includes the development of new semiconductor materials, their characterization and understanding of the physical properties under operating conditions. His work has been cited more than 4,500 times with an H-index of 39, and he is also inventor of 2 patents currently under exploitation. So in his talk, he will cover some basic concepts about the powerful electrical characterization technique named Impedance Spectroscopy, and how this technique can be applied into the analysis of the Perovskite solar cells. So the lecture will discuss the basic elements to obtain reliable measurements and interpretation of the fundamental equivalence circuits that represents this kind of technology. And he will discuss the meaning of the different resistive and capacitive phenomena that we can find in the technology. So please, Dr. Antonio, the floor is yours.
Thank you, Anna, for the invitation and for the kind introduction. Can you see the screen?
Yes, we can see it.
Okay. Okay, so well, thank you for inviting me to give this presentation on impedance spectroscopy of metal halide perovskite solar cells. Thanks to the Apollo project. And my talk will be basically divided in 2 parts. About half an hour, I will be discussing the basics of impedance spectroscopy. And then on the second part of the talk, I will talk about how we apply this knowledge to perovskite solar cells. So impedance spectroscopy is an electrical characterization technique which is useful for many different applications. So basically, what we need to have is to have a material that we can put some contacts on the sides, and we can apply some voltage, and we can measure some current. So basically, we just need to have a material and contacts. So for this reason, it's very simple technique to apply to a large array of materials and devices, like simple electronic elements like capacitors, resistors, has been applied in solar cells, LEDs, electrochromic devices, fuel cells. It has been very useful for understanding how electrochemical reactions work. It has been used in batteries and in dye-sensitized solar cells. So basically, the scope of the technique is very large, but often we find that the technique is not well understood. So this is why I will spend half of the talk just discussing about the basics. So if we focus on a solar cell, as explained by Uli, we just need to have like a semiconductor material and two contacts, one selective to electrons and one selective to holes. And depending on the external conditions, we will have different processes occurring inside the semiconductor. So for example, by interaction of radiation with the environment, we will have a background current that will generate electrons and holes. And these electrons and holes, they can recombine. So we will have only two currents which will be competing. Depending on the applied bias, at forward bias, we will be injecting current from the contacts into our semiconductor, or a reverse bias, voltage bias, we will be extracting this current from the semiconductor. When we illuminate the solar cells, there will be an additional source of current, which will be the photocurrent, which is here. So now we need to take into account the background current, the photocurrent, and the recombination current to understand if we will be able to extract current, or if we will be injecting current into the device. So the figure, as you may know, the figure of the merit of a solar cell is the JV curve, which is summarized here, just one example. So depending on the applied bias, the working mechanism inside the semiconductor will be different. And this is what we are trying to probe by using impedance spectroscopy in solar cells. We want to understand recombination currents. We want to know if there are problems with the contacts to extract the charge, or if the device is working well. The device is complex as it has several layers. Okay, so starting from this JV curve, we do impedance spectroscopy, which is a small perturbation technique. So in this technique, basically we can place ourselves wherever we want in the JV curve by applying a direct current voltage, a DC voltage. So basically, for example, here, we can apply a voltage here, and over this DC voltage, we apply a small AC perturbation. Okay, so this is the input that we introduce into our system, and the solar cell will operate, and we will be able to measure some current. Okay, so this is the output current that we are able to measure. Of course, we can change the frequency of this AC voltage, oscillating the voltage, and also we can change the applied DC bias. So basically, in this point, the solar cell will be operating, and recombination resistance versus photocurrent will have some values, but in this region, the operation mechanism will be could be different. Okay, so for example, here the recombination current is higher than in this part. Okay, but we can do the same thing. We change the DC bias. We apply the the small perturbation voltage, and we measure the current. So typically what we do is that we change, we place ourselves in several parts of the JV curve, and we modify the AC voltage over several orders of magnitude in frequency. Okay, the impedance will be a function of the perturbation we are introducing, and can be calculated by dividing the voltage by the current. So as you can find in typical textbooks, electrical impedance is the measure of the opposition that a circuit presents to a current when a voltage is applied. If we follow Ohm's law, the voltage, the resistance of the material, and the current that we can extract from a device, they are related, all of them. And when we apply a time-dependent signal like AC voltage modulation, we will define the impedance as the resistance of our system. Okay. The resistance of a conductor, of course, will depend on the conductivity of the conductor, on the path length of the charge to go from one contact to the other, and to the geometrical area of our contacts. The current response and the voltage that we apply will show a delay. Okay, so usually the voltage shows a lag, a delay in time with respect to the current that we can measure. And this is because in order to get a voltage, we need to build up the charge, and to build up the charge, we need to move the carriers inside the semiconductor. This delay, this lag in time, will be defined by the phase angle. Okay, and the impedance as a function of the frequency can be defined from the real part of the impedance and from the imaginary part of the impedance. The real part of the impedance is related to the resistance of the material, and the imaginary part of the impedance will be related to the capacitance and how the material responds to this applied voltage. This will be explained in more detail later. Okay, so what we need to measure impedance spectroscopy? We need a computer, a potentiostat, an impedance spectroscopy module, and a sample to measure. So in our lab, it looks like this. Here we have the computer, the potentiostat. There are some leads coming from the potentiostat going to the impedance spectroscopy module. They go to our sample, and they come back to the potentiostat. Okay, so here now I show you some actual measurement of impedance spectroscopy, where we have been done the measurement on lead halide bromide perovskite with this configuration, titanium dioxide, perovskite, spiral, and gold. This is the JV curve we get. We get very high VOC. And here you see 3 plots. First one, this is the complex impedance plot, where we represent the real part of the impedance versus the imaginary part of the impedance. Here we have the total impedance of the device versus the frequency. And in this one, we have the temporary variation of the applied voltage perturbation with respect to the current that we measure. So usually we start at frequencies, high frequencies of about 1 megahertz, and then slowly we go to lower frequencies. Now we are starting with the lower frequencies, and this is why here you can see the sinusoidal wave. And here, as you see, slowly and an arc is forming. Okay, I will discuss later about the meaning of these arcs. But as I explained previously, there is a lag in voltage with respect to the current. For impedance spectroscopy of perovskite solar cells, it's quite common to observe noise as we start to move to low frequencies. Okay, so also I need to mention that frequency and time are connected. One is the inverse of the other. So low frequencies, what it means is that it means long measuring times. So the impedance spectroscopy measurement can be very fast or relatively fast, the order of a few minutes. If you stopped at high frequencies of hertz or kilohertz, and it can be very slow if you go to frequencies of millihertz. Okay. Okay, so let's start developing the meaning of these arcs. So if we have the impedance of a conductor like this one, we apply AC voltage, and then we can define the current just by using standard physics. We can calculate the resistance as I showed you previously. So depending on the thickness of our semiconductor or our conductor, taking into account the conductivity and the area of geometrical area of the device. As we are applying an AC signal, this resistance can be defined as an impedance, and we can divide the voltage that we measure with our potentiostat by the current, and we will get this resistance. We will get the resistance of our conductor. So this in the complex impedance plot, I mentioned previously that the real part of the impedance is related to the resistance. In this case, what you could see is that if this is the zero, the data point you measure will be at a distance r to zero, and this resistance is the distance between zero and where you measure the data point. As you know, the resistor is usually plotted in this way. Okay. If instead of a resistor you have a dielectric material, so basically you have a capacitor. In this case, the capacitance using physics from textbooks is the dielectric, the permittivity of the material times the area of the electrode divided by the thickness of the material. You can measure that in impedance spectroscopy, again, by dividing the voltage by the current that you measure. And in this case, you will see this capacitor as a vertical line, because the capacitor does not let the current to go through. This term, the current will be, in the limit will be zero, so this goes to infinite. As this goes to infinite, this shows as a vertical line. Of course, materials are usually they are not only conductors and they are not only dielectric. So in the case of solar cells, we use semiconductors. So in many cases, we need to use what is called constant phase elements. These constant phase elements basically is a capacitor, which is not ideal. So this capacitor has this ideality factor n, and in the complex impedance plot, instead of looking as a vertical line, it looks like a tilted vertical line. If we continue with the typical elements and the response in impedance spectroscopy, as I mentioned, you can have a semiconductor where you have some type of conductivity, but also it behaves like a dielectric. So in this case, if you are measuring a bulk material, you will have this combination of resistors and capacitor in parallel. And a resistor and capacitor in parallel typically leads to an arc. So this is basically what we were looking at previously. And this arc has a time constant, tau, which is the product resistance by capacitor. Okay, let's continue with the next type of element. So we are building the complexity from just a pure material to a multi-layer device. So let's imagine now that we have two layers. The first one is conductor. Let's say, for example, the FTO of our solar cell. And these two will be the semiconductor of, for example, of our perovskite. So in this case, we would arrange the elements in series. First, the elements related to the conductors. This is resistor 1. And the elements related to the semiconductor, this RC. And in the complex impedance plot, what you see is that there is a shift, R1, related to the conductor. This is the series resistance of a device that we measure by impedance spectroscopy. And this arc will be related to the properties of the semiconductor. If we have more than one process, and we have, let's say, two layers, and both of them, they are semiconductors, or they are not purely conductors, or they are not purely capacitors, and the time constant of both of them are very well separated and resolved. So let's say they have different orders of magnitude in seconds for the characteristic time. In that case, we will see two arcs which are well resolved. This is usually not the case. So usually the different processes are coupled because electronic processes usually happen between the same time scale. So this would be different, for example, if we compare electronic processes with ionic processes. Ionic processes are typically slower. They could show at lower frequencies, and in that case, maybe it's possible to see two well-separated arcs, but that depends on the material. So one needs to be aware that there are different equivalent circuits that would fit the experimental data. So this is one of the main objectives when we start working with a technology, like when we started with organic photovoltaics, photoelectrochemical cells, or perovskite solar cells. One of the main objectives is to establish what is the equivalent circuit that represents well our system. Okay, and I need to say that for perovskite solar cells, this equivalent circuit is this general equivalent circuit is not totally clear yet. So I will show you one equivalent circuit that it works many times. Okay, but this will come in the second part. Okay, so next thing I need to tell you is that there are different ways to visualize the data, the impedance spectroscopy data. So far, I focus only in the complex impedance plot, where we have the real part of the resistance and the imaginary part of the resistance, and we see arcs. A different way of visualizing exactly the same data is by using the capacitance frequency plot. Okay, as you see here, capacitance and impedance are related. So if you know the capacitance, straight away you can calculate the capacitance. So these are two ways of visualizing the same data. And two well-resolved arcs lead to two plateaus in the capacitance frequency plot. This high frequency arc will be observed in the high frequencies. So this is the geometrical capacitance, so related to the dielectric relaxation processes of the semiconducting material. And this capacitance we observe at low frequencies is called excess capacitance is related to slow charging of your semiconductor. I will explain later the meaning of this capacitance in perovskite solar cells. Okay, so as I mentioned, there is some ambiguity with the equivalent circuits, and we need to use well-validated equivalent circuit. And there is a reason why one needs to be well aware of the literature. So here I show as solid points the data points that we measure by impedance spectroscopy. And the lines are the fitting curves using this equivalent circuit A and this equivalent circuit B. Mathematically, both of them, they perfectly fit or they fit reasonably well the experimental data, except for these data points in the low frequency, okay? But by now, let's forget about this. As I mentioned, we can use the complex impedance plot, we can use the capacitance frequency plot, and in both cases, the fitting is relatively good. Well, both fittings, they are not equally valid, because from these fittings, we will get useful information from our devices. For example, we can get the geometrical capacitance of the device in the high frequency region, or we can get the resistance related to, let's say, recombination of carriers or electropolarization. But there are different factors that we can measure. But here, once we do the fitting, we can see that the geometrical capacitance in this case is exactly the same for the two equivalent circuits, but all the other parameters that we are using, they are totally different, and they have different physical meaning. Okay, so it's very important that we use validated equivalent circuit and we understand the meaning of each of the elements of the equivalent circuit. Okay, so I need to say that for perovskite solar cells, the capacitive phenomena is well understood, but the resistances, they are not so well understood. So there are more work to do in this respect. So once we get these parameters, okay, these resistances and capacitance, typically what we want to do is to compare different cells to tell people why one cell is better than the other. And the other reason to extract these parameters is to obtain absolute values for, let's say, conductivity, diffusion coefficients, and so on. Okay, so the working diagram is the following. We obtain the impedance data, we choose the best model that represents our system, we check the fitting, that is good, and then we analyze the data and we extract the physical-chemical parameters. Okay, so now I'm going to show you one literature example that has nothing to do with perovskite. So let's say we have this material, this bark material, and we want to understand the conductivity of the grains. Okay, and so we have this is a polycrystalline material. We want to know how conductive are our grains. So we go to the lab, we design one experiment. For example, we can deposit micro contacts at different sides of our grain, or we can place contacts on the top of the grains. For example, in this contact here and this contact here, if this grain is very conductive, the conductivity could go through the grain, okay? And then we do the measurements. So this work by Rodwald and Meyer in 2000, for example, they showed that by using impedance spectroscopy here in the complex impedance plot, there was only one arc, and they attributed this arc to the conductivity on the grains. And as you can see, the values of resistances are very high. They are in the order of gigaohms. So basically, these grains are highly resistive. Okay, so if we then analyze all the grains, like for example, from this electrode to this electrode, and we apply a voltage across them, we will have some signal coming from the conductivity on the bulk, some information from the resistivity at the grains, and some information in the other side of the bulk. And in this case, they showed that they were able to see two arcs. The high frequency arc was related to the neighborhoods around the grains, and the low frequency signal was related to the grain. Okay, so this is just to show you something that is not a solar cell, but this is something useful to know all the different tools that you have for this technique. Okay, so if we then move to the response of perovskite solar cells, probably I don't need to mention much about perovskite solar cells. I will just mention that for the most of the work I'll show you here, we use methyl ammonium lead, and we use either the pure MAPI cell with iodide, or with the bromide. Okay, these are the main formulation we've been using. So then in the perovskite solar cells, you follow the talks this morning and the previous talk from Uli. You know that the devices are very complex. We have conductivity, electrical conductivity in the device, and by using impedance, we can try to understand the bulk properties of the material. We can try to understand the ion migration of either iodine or methyl ammonium. We can try to understand what's happened with the ions once they are close to the contacts. These ions, they can diffuse from the interface across, for example, the spiral OMTAT. And also these ions, in the presence of an electrical field and light, they can react with the contacts. All this can be detected by impedance spectroscopy. And as you can imagine, there are several processes, so the response is typically very complex. Well, perovskite solar cells, as you know, they are mixed electronic and ionic conductors. This has been known for a long time, from 1988, 1987 and 1998. There are some papers on the mixed electronical and ionic conductivity of perovskites. And then once we had the perovskites, MAPI, and all this family for solar cells, this has been proved as well later on. Also, these the ions, they have very important effects in the operation mechanism of the cells. So they totally change the operation of the JV curve by introducing injection barriers, and also by leading to chemical reactions at the contacts. And if I mentioned previously that when we use impedance spectroscopy, we want to see well-resolved arcs, the time constant of the process, they need to be well separated, okay? So for electronic transport in perovskite solar cells, is known that the carriers, they move very fast inside the bulk of the materials, with the diffusion coefficients in the order of 0.3 square centimeter seconds minus 1. But then for ions, the situation is different. They move slower, with a time constants of 10 to the minus 2 seconds, or methyl ammonium is larger, at least in the dark. The movement of these ions is smaller. And also we have electrochemical reactions happening at the contacts, and we detect these at the low frequencies, and this is very long times. time scale, so 10 to 1000 seconds. Okay, so here I show you the typical response of a MAPI cell, 18% efficiency device under illumination. And we apply, we measure impedance at 0 volts, at 0.7, at 1 volt, and at VOC conditions. Here, as you can see, there are different features depending on the DC voltage, and this is because the operation mechanism at the different voltages is different. So in this case, we are extracting most of the photocurrent, and in the impedance response, we see two arcs. We see one high frequency arc and low frequency arc. Now we know that mostly the high frequency arc is related to the bulk properties of the perovskite. So this is the perovskite itself. But in some cases, this resistance is influenced by the contacts as well. So this is why I mentioned previously that the resistances, they are not fully understood yet, but the capacitance, they are. The low frequency arc, this one, we are sure that these are related to the contacts. If we go to different applied DC bias, 0.7 volts, here we see how the size of the arcs is reducing. So here we have one arc with about 100 ohms, and the other one was 600, more or less, and now this is about 50. Here you see 50, and this is about 150. Here we see a distorted arc, and we see this thing which some time ago we didn't know what it was, and we used to delete it from the reported literature. This is what everybody was doing. So nobody understood this, and then people was just keeping quiet. Now we know that this is related to the chemical reactivity of the contacts, is also related to the hysteresis. If we go to 1 volt, and now we see the appearance of a hook, like a little hook, changing the quadrant, and at 1.1 volt, this hook is clearly like a different arc in this quadrant. So we now know that this is related to the contacts. Okay, so if we start with the more or less validated equivalent circuit, this is the equivalent circuit that we believed is the one that represents the most the physical processes that occur in a perovskite solar cell and the illumination when it's working. So we see the series resistance, and then we see this RC, this is the high frequency arc that we observe, and this low frequency arc connected to the contacts. So the main idea, I will explain this more in detail, but the main idea is that we can calculate the recombination resistance related to the recombination current that I showed you in the second slide, which is obtained by the addition of the two resistances, the low frequency one and the high frequency one. We can plot the recombination resistance as a function of VOC, apply DC voltage, we can change the experimental conditions, and then this helps us to compare different cells. For example, in terms of ideality factor, from this slope we can extract the ideality factor, or we can calculate the recombination current. So we get kinetic information from this curve. Okay, I will not go into detail. There will be plenty of results in this review that we are preparing, and hopefully will be accepted. If not in chemical review, will be somewhere else. but there will be plenty of results if you are interested in the topic. So I will move forward. You can also discuss the fitting results in terms of these characteristic times. This is the high frequency. You can calculate a characteristic time for the high frequency RC, so the product of R3 and geometrical capacitance, and also by the time constant of this RC as well. So in this work, they compare the low frequency one is independent on the light intensity, and the high frequency one depends on the light intensity. Okay, so if you are interested in the results, these results are published here. So just want to give you like a flavor of how you use the impedance, and then next I will show you some specific examples. Okay, so in this validated and simplified equivalent circuit, we have the series resistance as the shift of our arcs, the distance between the zero and the origin of the arc. So this is related to the connections, to all the conductors that we have in our device, the FTO, the gold, the wires, and everything. And then we have the high frequency arc, this RC. This is the RC. As I mentioned, the capacitance and the impedance are related. So this arc shows as a plateau in the high frequency region, and the low frequency arc is related to the contact. Okay, so I will not repeat this many times, but this low frequency arc also shows as a plateau in the low frequency region. Okay, so I will spend a few minutes in this slide. This is a slide where we compare the capacitance and the permittivity of the perovskite material as measured by different techniques. Okay, so here we have 18 order of magnitude in frequency in this axis. And by using different techniques, we can probe, for example, the interband electronic transitions. And with the band gap of the perovskite, we can probe optical phonon resonances at for example, using terahertz spectroscopy. And at lower frequencies, we have the dielectric relaxation processes. For example, reorientation of the methyl ammonium dipoles that they follow the alternating electrical field. So by using these techniques, static permittivity of 60 has been calculated in the range of kilohertz to gigahertz. Okay, so when we do the impedance spectroscopy measurement in the dark, the high frequency arc that we observe correlates quite well with the measurements that are obtained using all these other techniques. Okay, so this capacitance is related to the permittivity of the perovskite material. So this is a bulk properties feature of our material. As we apply the alternating electrical field, and it takes longer time to apply this electrical field, not only we change how the methyl ammonium molecules reorientate, but we promote ionic migration inside the perovskite material. So this is this onset in capacitance that here we see an increase is because the bulk material begins to change, and ions begin to go to the contacts. And at very low frequencies, there will be an ionic double layer close to the contact, and then we are probing the properties of the contact. So we are probing the electrode polarization of our device. In this ionic double layer, what we have is the typical ions close to the contact. The charge is compensated by the electrodes. And then we have the typical diffuse layers and so on. As we illuminate, not only we will have ions close to the contacts, but these ions, they will generate charges and they will modify the band bending as shown by Uli earlier. And there will be electrons and holes also piling up close to the contacts. And in this case, the charge at the contacts will increase that dramatically. So we will go to values of millifarads per square centimeter. And depending on the device configuration, at still lower frequencies are in the range of millihertz and tens of millihertz, we may be able to see noise, which is usually connected to the chemical reactivity of these ions in the presence of loads of charges, and with the photopotential generated by the semiconductor that are able to do electrochemical reactions. Okay, so now I will give you some examples, specific examples. I think I still have 10 minutes. So I'm going to start first with the bulk properties of the perovskite. Now, if we focus on the capacitance frequency plot, we can measure this capacitance frequency plot for 3 different types of perovskite: methyl ammonium iodide, bromide, and chloride. And this high frequency plateau, as I mentioned, is related to the dielectric relaxation inside the bulk of the material. So from here, we can get the permittivity values, and we can calculate the geometrical capacitance of our material. In this case, we take into account the electric constant of the material and the thickness of our semiconductor. Here, if the temperature is changed, is decreased, you will see that the permittivity values change with the temperature, and also in this plot, which is linear scale, is more clear to see that the 3 halides they have different permittivity values. Okay, so moving now to a different example. So for a long time, our group has been working with dye-sensitized solar cells. In these solar cells, we have titanium dioxide semiconductors, some contacts, and ionic electrolyte dissolved in liquid, typically. And in this system, it was well established, the general equivalent circuit model, and it was very often observed the signature of diffusion of carriers. Okay, so I will not go into the details, but the system was very well understood, and it was clear what was the meaning of each of the arcs. This was the general equivalent circuit. And depending on the applied voltage, we could see 3 arcs, or we could see this 45-degree angle with this type of vertical line. Okay, and I need to tell you that this is the typical signature of diffusion of carriers inside a semiconductor. So the theory was well developed. And in this case, the diffusion, as I mentioned, is observed as a 45-degree angle. There is a kink in this curve, and then there is like a vertical increase in the capacitance. This imaginary part of the impedance is increasing almost indefinitely. Okay, so for a long time, we were wondering why, if perovskite solar cells are mixed ionic and electronic conductors, why we were not observing this signature of diffusion. Why? And the answer was simple, and it was that we were observing the mixed electronic and ionic current, and as they were competing, they were both highly intermixed. So then what we did was to design a device architecture where we would minimize the electronic current. So we use methyl ammonium lead bromide monocrystals without spiro. They were directly grown on titanium dioxide. Because they are monocrystals, they are the doping density is very low. We chose crystals that they were very thin, between 1 and 50 micron. And we use conditions to minimize this current. So we would use 0 volts DC bias, and we use dark conditions. And if we fulfill all these conditions, we do see the signature of ion transport and accumulation. So this red path that we observe here, this is the 45-degree angle observed previously in the sensitized solar cells. And this vertical line is the accumulation of ions that typically happen at low frequencies. Okay. So from this data and modifying and making a batch of different thicknesses for the monocrystals, it is possible to calculate the diffusion coefficient of the ions inside the perovskite material. And in this case, it was giving values of the 1 to the 10 to the minus 8 square centimeters seconds minus 1. Okay, the response always depends on the device that you've got. So this is one of the reasons why it's so hard to propose a general equivalent circuit. If we add a spiral layer at the end of the perovskite, now we don't see the accumulation of ions anymore. Now we see that we still see what it looks like a 43-degree angle line, but now we don't see the accumulation of ions, but we see this arc. And this is a typical absorptive impedance when we have ions that are crossing one layer. Okay, we've used this knowledge recently to make memory stores. And here we have the response of 2 different memory stores making with RP perovskites using P.PSS and silver as a reactive interface with the perovskite, and spiral layer as a layer that lets the ions to go through. And here, as you can see, the response is totally different. When we have the reactive interface perovskite silver, this is the top graph here, we see the appearance of this hook. I mentioned previously that this was related to the chemical reactivity of ions with the contacts. We get this signal very, very reproducible, and we know that it's not an artifact. And when we place a spiral layer between the perovskite and the silver, now we see the absorptive, well, first of all, we see the high frequency, this spiral is not doped, so it's highly resistive, so the high frequency arc is related to the spiral itself, and now we don't see the appearance of the hook, because the system is, what we observe is the absorption of ions going through the spiral layer, and this is why the system is working as a memory store. I cannot go into the details because I think I'm running out of time. I'm not sure I've got how I'm doing with time. I'm a bit lost. Okay, so basically I need to start finishing. Okay, I was reading the comment. Okay, so I will go very fast now. So I want to check the interfacial properties. Basically, I mentioned already about the double layer capacitance, so there's no need to go into much detailing here. But at the time when we published these results, we were surprised to be able to apply electrical models typically used for liquids to devices that are prepared in the solid state. Okay, and this is because the perovskite is a very good ionic conductor. When we illuminate, we observe the electrode vaporization. Some modeling results like this from Martin Newcomb and those shown previously by Uli clearly show the mixed electronic and ionic nature of the interface. And this is why we see that the interfaces are being charged. And to finish with the contacts, we observe the signature of the reactivity. For example, in this device, we use methylammonium lead bromide cells without the spiral, so we promote the reaction of iodines with gold. And in this case, we start observing loads of noise in the low frequency region, and we attribute this to the chemical reactivity. We have done similar experiments with silver, and we observe also the signature of noise. How the results from impedance are very important because how the interfaces are being charged are totally connected to the hysteresis phenomena. Okay. And I'll give you one more example and then I can stop here. But for example, we can study, one of our colleagues studied the effect of water when we have a complete device, a monocrystalline device. We know that water generates an adduct, which is highly conductive, and a second water molecule leads to degradation of the device with formation of lead iodide, and our colleagues clearly showed that if the device was dry, the capacitance values and the illuminations, they were very small, but if the device was wet, the capacitance values, they were very high. So this basically means that the water is going to the external interfaces and they are reacting there. Okay, so just some final remarks. We can distinguish between reactivity and noise typical from impedance by using a range of precautions. So use Faraday cage, shield connections, use low noise potentiostat, stable light sources, and so on. And also, it's very important to think about how you want to report your impedance spectroscopy data. Okay, I have no time to go into detail. Hopefully, you will be able to read about this soon. With this, I just want to say that hopefully I showed you that impedance spectroscopy is a very powerful tool. Interpretation needs to be based in well-supported equivalent circuits, and for the moment, in impedance spectroscopy of solar cells based on perovskite, they are not totally established, but we are getting there. And also, when you report the results, you need to be careful how you do it, but I didn't have time to discuss about this. With this, I would like to thank all of you, and thank you for your time, and I'm sorry for running a little bit slow. Okay, thank you.
Thank you, Antonio. Thank you very much. I just posted on the chat the link of Google Forms for the quiz, as well as you have received it at this moment by email as well from the Apolo Summer School, the quiz session for day 1. Mm-hmm. You have at this moment until 5 o'clock to resolve all the questions of the quiz. And that's it. If you have some questions or some issues with the Google Forms, please send us an email to the organizations. Remember, I will remember by the chat my email just to inform you if you have some issues. That's it. Thank you very much.
And if anyone has any question, can ask me directly later or by email or
Yes, Antonio, you already have a question here. So you decide if you want to write it or you want to say it. The question is, thanks for the lecture. It's a two-wire measurement. The cables that set the voltage are the same ones that they call it the current, or is it a four-wire measurement?
It can be done both ways. Okay, we usually do it four-wire measurements.
I think that there is no more question right now, but Antonio, if you can wait for a few minutes just to see if there is another question.
Okay, yes. Great, thank you.
Okay, I think there are not more questions for you, Antonio. Thank you very much.
Okay, thank you very much.
For your time. So the session will be closed right now. Remember that you have until 5 o'clock to answer the quiz. See you tomorrow at the same time. So if you have some issues as well, send us an email, please, and we'll try to answer you as soon as possible. So thank you very much. So my pleasure to be here. So please, Anna, your time.
Okay, thank you, Joan. Thank you very much for all the participants to be here during the day. I think that we had a lot of interesting presentations, and of course, if all of you have some questions or want to speak directly with the speakers, you will have the information about the contacts very soon. So thank you very much, Hugo. I don't know if you want to say something before closing.
Yes, good afternoon to all. I would like to acknowledge all the students that were on today's session. I think you learned a lot. They've been very interesting, and they went deep into the knowledge of the solar cells. So I hope it has been good to all of you, and I also would like to thanks to all the speakers today for the very high level that were given in today's presentations. So I see you all tomorrow, and good luck with the quiz.
Thank you, Hugo. Manuel, do you have to say something before closing?
Well, no, it's
So I said in the beginning, well, I hope you enjoyed and don't miss the next lectures. You know, tomorrow we have very interesting ones about light trapping, light management. So, well, hope you enjoy it, and see you then tomorrow.
Okay, thank you very much, and have a nice rest of the day and a nice quiz. And see you tomorrow. Bye-bye.
Bye bye. See you tomorrow.